This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 06. Pump curves, system curves, and affinity laws. Where the pump curve meets the system curve, and how that operating point shifts when we change pump speed, impeller diameter, or piping. Topic 05. Sized a pump for one design flow. Topic 06. Zooms out. A pump doesn't pick its own flow. It's set by where the pump's head versus flow curve meets the system's. The pump curve falls as flow rises. The system curve rises. They cross once, the operating point, which governs everything from efficiency to motor sizing. 3 questions show up almost every cycle. 1. Given the pump and system curves, find the operating point. 2. The speed changes. Predict new flow, head, and shaft power with the affinity laws. 3. 2 pumps in parallel. Explain why combined flow falls short of double. Each is a clean point if you know the moves. Recognize the pattern. If the stem hands you a pump curve, a minus BQ squared, or a system resistance, Z static plus CQ squared, you're setting up an intersection, not a single point energy balance. Other tells: 2 pumps in parallel or series, a speed change, an impeller trim, or a throttle valve closing. Each moves the pump curve, the system curve, or both. Build the table before any algebra. Left column, operating point, shutoff head A, curve coefficient B, static lift Z static, system resistance C, then Q op, H op, and pump efficiency. Right column, affinity laws, the 2 speeds, the speed ratio R, and the outputs Q2, H2, and P2. Fill what the stem gives, derive the rest. The pump curve is a downward opening parabola. Constant A is the shutoff head, the highest head, and zero flow with the valve closed. Constant B sets how steeply head drops as flow rises. The system curve opens upward. The intercept Z static is the static lift plus any fixed pressure rise, independent of flow. And the coefficient C lumps every Darcy-Weisbach and minor loss term from topics 03 and 04. To find the operating point, set the 2 equal. Worked problem. Pump curve. H sub P equals 80 minus 0.05 Q squared. Head in meters, flow in liters per second. System resistance. H sub sys equals 20 plus 0.08 Q squared. Find the operating flow and head. Populate the table, set the curves equal. Populate the table from the 2 curves, A, B, Z static, and C. Now the critical step, add B and C, never subtract. Q squared op equals A minus Z static over B plus C. The square root gives Q op 21.5 liters per second. Head comes next slide. Walk it. Set the 2 curves equal and collect the Q squared terms. And this is where almost every wrong answer comes from. Add the coefficients, because the curves resist each other. Solve for Q op, then substitute back into the system curve for the operating head, 56.9 meters. Verify with the pump curve. Both agree. Final answer, Q op, 21.5 liters per second. H op, 56.9 meters. Choice A. The classic trap is choice B, subtracting the coefficients instead of adding. The 2 curves resist each other, so always add. Affinity laws. 3 ratios. Flow scales linearly with speed, head as the square of the speed ratio, power as the cube. Exponents 1, 2, 3. Flow, head, power. Worked example. A pump runs at 1750 RPM, delivering 200 gallons per minute at 80 feet of head and drawing 15 horsepower. Speed climbs to 2100 with the same impeller. Find the new flow, head, and power. Speed ratio R is 1.200. Flow times R gives 240 gallons per minute. Head times R squared, 115.2 feet. Power times R cubed, 25.9 horsepower. A 20% speed bump raises shaft power by almost 73%. That cubic exponent is why variable frequency drives save serious energy on the way down, and why an unplanned speed increase can melt an undersized motor on the way up. Two identical pumps in parallel share the same headers, so each sees the same head and carries half the total flow. Substitute Q total over 2 into the single pump curve. The B coefficient divides by 4, not 2. Solve against the system. Q total is 29.3 liters per second versus a single pump baseline of 24.5. The second pump bought only 4.8 more, a 20% gain, not 100. The rising system curve absorbs most of the extra capacity. Series is different. Same flow through both, heads add. Reach for it when you need more head, not more flow. 5 traps. 1. Subtracting the Q squared coefficients instead of adding. Both resist, so add. 2. Assuming parallel pumps double the flow, the rising system curve absorbs most of the gain. 3. Confusing series and parallel. Same suction header is parallel, discharge feeding the next inlet is series. 4. Scaling head linearly or power quadratically with speed. The exponents are 1, 2, 3, flow, head, power, and misapplying the cube law undersizes motors. 5. Operating far from BEP and assuming only efficiency suffers, past 10% off, radial thrust, vibration, and NPSH required, all climb fast. 5 takeaways. 1. Operating point shortcut. Q equals the square root of A minus Z static over B plus C. 2. Parallel pumps add flows at equal head, but the rising system curve clamps the gain well below double. 3. Affinity exponents 1, 2, 3 for flow, head, power. 4. Throttling steepens the system curve. A variable frequency drive saves energy because power scales as the cube of speed. 5. Operate within 10% of BEP. Next, Topic 07. Flow measurement. Venturi, orifice, Pareto.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.